So in fluid statics, the first thing is to study about the various pressures. So there are many pressures like absolute pressure, gauge pressure, vacuum pressure, vapor pressure. So, so this is the small graph to differentiate the various pressures. So the reference pressure, or also called the vacuum pressure or absolute pressure, is the pressure at which the value of the pressure is 0 bar, and over that if we have some pressure between the 1 bar and to the 0 bar, it's called vacuum pressure. So which is the 1 bar means this is the atmospheric pressure where we live. So below this pressure, whatever it's called is called as the vacuum pressure. But so vacuum pressure are calculated as minus 0.8 bar. So if it is minus 0.8, it is called vacuum pressure. But when we consider it with respect to the reference or the absolute pressure, so that means it is 0.2 bar. So this is a absolute pressure, this is a vacuum pressure, and this 1 bar is called the atmospheric pressure, and over this 1 bar if we consider any pressure, it's called gauge pressures. Okay, so these are gauge pressures, and if this pressure 2 bar is considered with respect to this absolute, which will be 3 bar, and that 3 bar is called as absolute pressure, just 2 bar is called gauge pressure. Okay, so there are units for pressure is called Pascal or Newton per meter square or PSI also called, and vacuum cleaner. So the suction which creates the vacuum pressure is called vacuum pressure, and they have negative value as it's called like this. And one atmospheric pressure is 1 bar, which is equal to 100 kilopascal or 10 power 5 pascal or 10 power 5 Newton per meter square, and in exact value it is 101325 Newton meter square. So from ideal equation, that is PV is equal to MRT, if these values are constant, so we will basically use absolute pressure and absolute temperature. So what is absolute pressure? Absolute pressure with reference to the absolute vacuum pressure is called absolute pressure. So gauge pressure is equal to atmospheric pressure plus additional change in pressure, means positive pressure. Vacuum pressure is atmospheric pressure minus the change in pressure, and absolute pressure is atmospheric pressure plus gauge pressure. So from this uh, vaporization we will discuss, will come here. So the vapor pressure is the pressure due to the vapor from the liquid surface. It is a phenomena of a vaporization. So when the temperature increases and the pressure on when the vapor pressure on the pressure over the liquid surface is greater than the pressure inside the liquid surface, then the vaporization happens. So the vaporization, the pressure on in the vapor when it is greater than the pressure over the surface, means on the surface, at that given temperature, at that time the vaporization happens. If the both the pressures are same, at that point the boiling will happen. Okay, so that is what written here. And what is fluid statics? So in fluid statics there are no relative motions, then that means the body is at rest, and from this Newton's law of viscosity, the law is the drag stress is equal to viscosity times the velocity gradient. In fluid statics where the motion is at rest, at that point the velocity gradient is 0. As this is 0, the drag stress or the shear stress in the fluid motion is 0, because there is no motion, so there is no stress at all. So the forces involved in static fluid are pressure force or gravity force. So these forces are there because we study fluid statics because we want to study the energy inside the static body. So if we have a water at some position, it has a gravitational energy, potential energy, or the surface where the static fluid is there. At that surface, that surface faces the pressure due to the weight of the liquid body. Okay, so basically the two forces are applied, pressure force and gravity force acts on the static fluid. Okay, then let's talk about the hydrostatic law. So what is hydrostatic law explain? So hydrostatic law says that it helps us to calculate the pressure at given point inside the fluid. So that pressure is equal to rho gz. Rho is density, gravity, then the z is the height, the depth of the particles. So at this point the pressure is this. So pa is equal to atmospheric pressure plus the pressure inside the body, inside in this depth. So the pressure gradient can be described as dp by dz is equal to rho g, which is equal to the specific weight. Okay, if we are calculating the pressure above a certain point, at that time we need to minus the pressure. So if you have to calculate the pressure here, and here is the atmospheric pressure, then atmospheric pressure minus this value will give the pressure at this point. Okay, so next is we will see about the hydrostatic paradox, which is a paradox, like why it is happening. We will see that later. Okay, we will see it right now itself. Hydrostatic paradox. Yeah. So if we have different containers, something like this, different containers. So what are the questions? So dependence of the hydrostatic force with respect to the P and A. So you'll see that. So as you can see, there are different uh, shapes of the container, but for different shape, that means the weight of the liquid will differ here, but this area is same in all these three cases. So the area is same, and then we calculate the weight. As we know, the containers are different, so this container will have the highest weight and this will have the lowest weight. But will the pressure will be same in all these cases? The answer is yes, because this the height of the liquid is same for all the cases, and the pressure doesn't depend upon the shape of the container, okay, and the area. So the pressure is equal to rho gz, the z is the height, so it only depends on the depth. That means the pressure in all this case will be same, and as the area is also same in all these cases, the P times A is equal to force. The pressure force or the hydrostatic force will be same in all these three cases, okay, irrespective of the shape of the container. So the dependence on the hydrostatic force with the PA is this. Yes, it depends on the pressure as well as the area, but the reverse is not true. The pressure doesn't depend upon the area as well as the hydrostatic force. Okay, so this is the answer. So does force change with respect with the shape and height of the filled container? Yes, for the height, no for the shape, because Z is one of the parameter to find the pressure. So the proper container F is equal to W, we will see that. So there are some cases in which we have a container like this. What is the pressure here? The pressure is rho g z1 plus z2. It doesn't depend on this cross section, just it depends on the height. So we will get the hydrostatic force for this case. But what is the hydrostatic force for this case? Again, P is equal to rho zg. It doesn't consider this transaction, just the depth. We will find the hydrostatic force. This is the interesting case. We will see. This is just a proper cylindrical container. So for this thing, the hydrostatic force is P times A, and P is rho g z times A. So z times A is the volume. We will get the volume, and as we know, the rho times V is equal to mass. So mg. That means the hydrostatic force is equal to weight in this case. But let's consider this kind of container. So as we know that hydrostatic force are applied all over the surface, but these two surfaces as they are parallel, so the hydrostatic forces get cancelled. Okay, that's why we only consider the bottom hydrostatic force. But while for this case, as we see that the container is curved like this, the hydrostatic forces are always normal to the surface. So we know that this x direction the forces will get cancelled out, while the Fy will get added up to the hydrostatic force. So therefore the net force along the y direction will be hydrostatic force plus the Fy. That means the weight of the liquid will be equal to the Fy. That's why the weight is greater than the hydrostatic force. But when the container shape changes like this, we see that hydrostatic the total weight, that is the vertical force, is hydrostatic force minus the vertical force, and at that time we see that hydrostatic force is equal to weight plus Fy. at this case the weight is less than the hydrostatic force. Okay, so these are some differences we need to know. So how would be a small tapered container? So just we say that for this kind of container the weight is less than the hydrostatic force, or for this kind of container the weight is higher than the hydrostatic force. So this is the hydrostatic paradox. So let's talk about the Pascal law. So here is the Pascal law. So what does the Pascal law say? The intensity of the pressure at a point is same in all directions. The intensity means the the action of the pressure is not directed to particular directions. It is everywhere same. As we have to know that the pressure and the stress are both tensor quantity. That means they have magnitude and direction, but the direction is not fixed. The direction is not fixed. That means it doesn't have any direction. In other case, so it's like a time. The time doesn't have any particular direction. It is like all the way. So the pressure at all the direction are equal. Okay, that's what the Pascal law says. That means the intensity of the pressure is same in all the direction, and the pressure is a tensor property. So next is manometer. So what is manometer? Manometer is basically a device to calculate the pressure inside the fluid. So that is why we need it to calculate the pressure. There are basically two types of manometers. One is a simple manometer and another one is a differential manometer. So in simple manometer there are three types: piezometer, U-type manometer, single column manometer. And then we have again two types. So what is the piezometer? It's the simplest manometer. Is used to calculate the gauge pressure. That is, the gauge pressure is called atomic pressure plus the additional pressure. It is not used to calculate vacuum pressure. It is not capable of calculating vacuum pressure, and it cannot calculate the very high pressures. So this is how the piezometer looks like. This is the water flow. The discharge is like something like this, and in this a small tube is applied. So the cross section seems like this. So this is center of the tube, and if you want to calculate the pressure at this point, so what we have to do is, sorry, at this point, as the flow is along this out of the center, so pressure at this point will be equal to atomic pressure plus the height. Okay, then we will know what is the pressure of this fluid going here. But why we cannot calculate the vacuum pressure is because the vacuum pressure is below the center. If there is a vacuum, then means it is below the center of this geometry. So we cannot calculate the vacuum pressure. And for a very high pressure, this water level will be very high, and it's not practical, or it is not feasible to have a very long tube to calculate the pressure. For that, we have another methods that is called U type of manometer. U type manometer. So this is basically used to calculate the vacuum pressure as well as the gauge pressure. So and can be used to calculate very high pressure also. So this is how the U-type manometer looks like. This is like U-type. So this is where the fluid discharge or flow through. So as this fluid is flowing through, we want to find the pressure at this point. And these are fluid which has higher density. For example, mercury. So the pressure at this point will be P plus rho GH, which is equal to, and we are basically taking, this is the cross section, this is the interaction. So we are equating the pressure at this point as well as this point, because at this point both the pressure should be same. So at this point the pressure is P plus rho GH, and then which is equal to atomic pressure plus this side, the density of the mercury G and H1. So from as we know all these parameters, we can find the pressure at this point. So this can be used for vacuum pressure, because if there is vacuum in here, this level will be below this point. This pressure level will be below this point, and that point also we can calculate the pressure at this point. And this can be used for very high pressure, because the density is very higher than this fluid, so at that point the change in pressure for very high pressure can be calculated because it is a very high density and moves slowly. It doesn't we don't need very high tube to calculate. Okay, and next is the single column manometer. So this is the single column manometer. In that there are two types. One is the vertical type and second one is the inclined type. So the reason for its uses, and can it be used for high or low pressures? So basically the reason for using the manometer is because it is more sensitive device. So what is the meaning of accuracy versus the sensitivity? Sensitivity accuracy means the closeness of the actual value. Closeness, like if you are calculating something, is our calculation really close to the actual correct value? So that is called accuracy. And sensitivity is the how does the result change with respect to the change in parameter, or if there is a small change, if a small change can be calculated accurately. So these are the another thing. Can the small, if there is a small fluctuation, can that fluctuation be calculated properly? So that is called sensitivity. So this single column manometer are basically used for when the pressure is not very high. That means it is not used for high pressures. It is only for use for low pressure, but the change in pressure is very frequent. At that case, these single column manometers are used. So for vertical column, this is the situation. Uh, we will see that why the inclined are used. So this is the single column manometer, as you can see. So we want to calculate the pressure at this point. So if you want to calculate at this point, this is other fluid with higher density, like for example mercury, and there is another fluid here. So when there is a change in pressure, so this fluid level will increase. So we will use a single calculator to calculate the fluctuation only in one side here, not here. So the change in pressure here will change the length of the liquid here. So as the change in pressure is equal to rho g y, we, due to the when we calculate this distance y, we will know about the change in pressure. So for very frequent change in pressure, because this is a large area, so we won't be able to basically calculate the change in pressure here, but as this is a thin tube, the depth level can be measured. So from this we will know the pressure at this point. While we use another way, the single column manometer, for inclined thing. So this is basically used to calculate the fluctuation of the pressure, and the inclined is basically more sensitive. We will know why it is more sensitive. So as you know that the relation between this length and the y length is L is equal to y sine theta. That means at sine 90 is equal to 1. That means at sine 90 is 1. If we have a smaller value, that means the length will be high. This length will be high. So the lesser the theta, larger the length. So when there is a small fluctuation, even at that point, the length, this will be very high. So when this measurement is high, we will know, we can calculate this length better. If we can calculate this length better, we can ultimately be able to calculate the pressure change here better, because y is the function of L. So at that respective with that respect, we can calculate the change in pressure more accurately. And basically we are not considering the change in this part, and due to that there can be some error, but the error percentage is, the equation for this is like this, but we are able to accept errors which are less than 5%, that is acceptable level. And the pressure at this point will be P plus rho gh is equal to P atmosphere plus rho gh L sine theta. So this is the cross section in interface. So at this point we are calculating the pressure which should be equal on the both sides. So that's how we get. So next one is the manometer. Sorry, differential manometer. So this kind of manometers are basically used to calculate the differences between the 2 points. So For example, like this is the basically inverted U-tube, and this is the normal U-tube. So the change in pressure can be calculated from this depth, and this U-tube, this fluid which is different density. So this U-tube will have higher density with respect to the flow of the fluid, and this fluid will have lesser density than the flow of this fluid. The reason behind this thing is, if there is a high pressure, if there is a fluid going there, if the liquid is denser than this liquid, the change here will be less if there is a high pressure here. But if you have a low pressure, inverted U-tube can be used, which has a lesser density than the fluid going here. So if there's a low pressure, this low density fluid will react much better, and at that point we will get a more high difference. From this high difference we can find the pressure differences. So this is the reason the inverted U-tube is more sensitive than the U-tube. So, and these are used on application basis. For example, the underground pipe or aeroplane roofs, they use inverted U-tube because the fluctuation is high and the pressure is quite low. And the from this inverted differential manometer, we can basically find the direction of the fluid flow. Given that the pipe has some friction, it creates pressure difference. So if this is a pipe, there is a friction on the walls, it creates, so from this to this point the speed will be low, so therefore the pressure will be low. So if we know that PA pressure at this point is greater than PB, then we know that pressure fluid flow is from A to P. So this is also a useful thing from the differential manometer. And the next topic is buoyancy and flotation. So what is buoyancy force? So buoyancy force is basically the weight displaced. Uh, it's a liquid. It's the weight of the displaced liquid. So if we immerse object like this, so the buoyancy force is basically the weight of the displaced fluid. Means the amount of weight displaced due to this area occupied. That is called buoyancy force. So when we immerse a body or a flotation body, the buoyancy point is basically the centroid of the immersed body, while G, which is a centroid, is a basically geometrical center of the whole body. So always for the floating body, the buoyancy point is below the centroid or the gravitational center. Okay, and the centroid point of the geometrical center, at that point the weight is always downwards, and for buoyancy force is always upward. A body may float in liquid in fully immersed state or in partially immersed state. Okay, that's because of the specific gravity. If the specific gravity is 1, the body will be immersed and will be floating at the same time. If the specific gravity is less than 1, the body will be floating. So we will compare the buoyancy forces in the after coming diagram. So from this diagram we see that this body is immersed and there is hydrostatic forces or pressure acting upon this body. The side pressures are basically cancelled because they are equal and opposite, so only the vertical forces are applied here. So what is the total hydrostatic force acting on this body? So the pressure on this plane are rho gx and rho gl plus x. So the hydrostatic forces are P2 times A minus P1 by times A. If we calculate it, the answer is rho g LA, which is basically the weight of the liquid displaced. So this hydrostatic force is nothing but the buoyancy force. That's what it's making it float inside the water. If the hydrostatic force here was higher than this, that means the liquid weight is higher, sorry, the body weight is higher, and it would be sitting here in the bottom. It won't be floating inside the water. Next one is to compare the buoyancy forces. So as we can see, all these three cases, in all these three cases the buoyancy force is same. the weight of the liquid displaced is same in all the cases. In all these three cases, the buoyancy force is nothing but the liquid displaced. As this body is completely immersed, the buoyancy force is nothing but the liquid displaced. If all these three are in same shape, the liquid displaced will be same. That means all this force will have same buoyancy force. But it depends upon the specific gravity of this body, which one would be floating higher than this. From this case, we can say that the specific gravity is much higher in 3 than this 1 and 2, and you can see here also. As you can see in case 1, the specific gravity is 30%, only 30% is submerged. In 2 is 60%, 3 is 60% is submerged, and 3 and 4 are basically 1. We cannot see exactly which one is high or small. And 5 and 6, it is greater than 1 because we cannot calculate specifically which one is how much. Okay, so we have discussed the reason behind the flotation and the comparison of flotation with respect to the specific weight or specific gravity. And as we already discussed the net hydrostatic force on the cylinder, this is the net hydrostatic force on cylinder. Then we will move on to the metacenter. So what is metacenter? So as you can see from this picture, so this the metacenter concept is only considered for the floating bodies. Okay, basically only considered for the floating bodies. So a metacenter, we will discuss what is it. So when there is a small tilt in the floating body by a small angle at theta, the body then displays a simple harmonic motion. That means it swings like this, simple harmonic motion. And metacenter is a point about which the body starts to oscillate. So if this body is tilted and it starts to oscillate, so this will also oscillate about a point. So if you create oscillation of a particular thing, you will see that it oscillates at this point. So how do you find this metacenter? So the interaction of the buoyancy force direction to the normal axis. So when this body is displaced or tilted, so the buoyancy point is here. If you make a direction, normal direction upward, and when it intersects with the body normal axis, so this point is called the metacenter. So at about this point only the body oscillates, and this body can be inside or outside the body. As for this case, it's inside. If it is a different body, the metacenter can be outside here above. And if the body is immersed, the metacenter will be below the centroid as well as the buoyancy point. It would be like here below. And what kind of motion? It is the simple harmonic motion. Location of the body with respect to the float and mass. For the float, the M will be above the G and B. For the immersed, it will be below the G and B. Next one is the stability of the floating body. So, floating body we are going to talk about with respect to the ship. So, if consider this as a ship. For the ship, as we know that the ship engine room is at the bottom, and it is purposely kept so that the gravitational the center of the gravity is below the buoyancy point, so such that the gravity is always downwards and the buoyancy force is always upward. So when there is a tilt due to the ocean motion, what happens is that the change will be like this. The buoyancy force point will move while this gravity center will be always in the same point. At this kind of situation, there is a couple, weight is here, the buoyancy force is here. So when there is such a condition, the nature of the body is such that it will create a restoring couple which will bring back the stability. So that's how the floating body keeps itself stable. Okay, and next is the center of the hydrostatic pressure force. So the hydrostatic pressure force, there are two types. One is the for inclined plane or immersed thing. If the plate is immersed completely like this, we know that hydrostatic pressure are linearly different like this. So For a given plate, this is the center of the gravity or the geometrical center. But if you want to calculate, if you want to assume a point where the total hydrostatic force acts on the plate, we can basically calculate from the centroid of this pressure force area, and this centroid, when we direct it to the plate, and this point will consider as the hydrostatic center, pressure center for this plate. And if we have inclined plane like this, again the centroid of this whole area will be taken and will be directed to the plate, and this point becomes the hydrostatic central pressure force. So the force center is basically an assumed quantity, which assumes that the whole hydrostatic force is concentrated at this point. Okay, so does the hydrostatic force change linearly with the depth? Yes, it changes linearly with the depth, as we know, rho gh. And how to identify the net hydrostatic force, as we know, from the centroid of the force area. So is the center of the pressure an assumed quantity or exact quantity? Is an assumed quantity. And the another one is the curved plane. So this is a curved plane like this, and there is a liquid here, and we are considering only the half of the plane here. So what is the, so how P varies with respect to the depth of the cylinder cross section? As we know that the pressure here will be less than the pressure here because the depth is higher, so the pressure will be higher here. Okay, and if the Fy is greater than Fix pressure force, which force is dominant here? So if the Fy is very high, as we have discussed from the earlier situation, if the Fy is very high, that means it is the buoyancy force. If the Fx is higher than the Fy, it means the weight of the liquid here is very high. So that is the difference. And the net F is displaced liquid weight. So the net hydrostatic force can be calculated by adding the forces, first resolving this pressure into x and y forces, and then adding it, you will get the force like this. If the direction is below the cylinder, it means for this case it is the buoyancy force. Okay, and I think we have covered it. We will see next for the fluid dynamics, fluid kinematics.